Section 6.8 in the book talks about the derivatives and integrals or antiderivatives of inverse trig functions. We are just looking at the derivatives first. So if you have not read through the review 6.8 inverse trig function PDF that I posted yet, please make sure you do that first, because there's a few things on there that you're going to want to look at before you can follow how we find this derivative, okay? So what I'm going to do is I'm going to go through and develop the formula for the derivative of tangent inverse of x, and hopefully after seeing that, it makes sense and in such a way that if you wanted to prove or derive the formulas for the derivatives for the other 5 trig inverse functions, then you would be able to do so using a similar method, okay? So we have y equals tangent inverse of x, and the issue is we don't yet have a formula for the derivative of tangent inverse. So just like we did with the exponential functions in 6.3 and 4, we are going to rewrite this equation in such a way that we can take the derivative, and we'll use implicit differentiation for that, okay? Because what I'm going to do is I'm going to take the tangent of both sides of this equation, and I'll have tangent y is equal to, and then tangent of tangent inverse x is just x. Okay, so now I can take the derivative with respect to x, all right, implicitly, and I get secant squared y times y prime is equal to 1. Okay, and then solving for y prime, I'm going to divide both sides by secant squared. Dividing by secant squared is the same thing as multiplying by cosine, so then I get y prime is equal to cosine squared of y, which is equal to cosine squared of, and then y is equal to tangent inverse of x. A couple reasons we can't leave this in terms of y. One is that because the original function is explicitly defined, we can't have any y's left over, or we need an explicitly defined derivative. The other is because tangent inverse might not be equal to y. It might just be part of an expression somewhere, so we can't just assign it a new variable that wasn't in the original problem. So there may not be a y written to start with. So that's why we need to put it back in terms of x. Okay? Now from here we do want to further simplify. To do that, and I went through an example of this in that PDF, but I'm going to start by drawing a triangle. Okay, drawing a little reference triangle here. And this right here has an input of a ratio and an output of an angle. Okay, and so theta is tangent inverse of x. If theta is tangent inverse of x, then that means I can label this right triangle as x on the opposite, 1 on the adjacent. And then to evaluate cosine squared of this, all right, what I want is for cosine, I want the adjacent over the hypotenuse. So I do need to find this third side. Okay, switch colors here. So using Pythagorean theorem, this side right here is root 1 plus x squared, and then that's, let's see, so then you don't need to write this in between step, but we have cosine squared of theta, okay, which is equal to, and then cosine is 1 over root 1 plus x squared, so 1 over root 1 plus x squared, and then that quantity is squared, okay, and then when we square that, we get 1 over 1 plus x squared. So 1 over 1 plus x squared is the derivative of tangent inverse of x. Okay, now going through the same process where we apply the trig function to both sides to undo the inverse, and then take the derivative implicitly, and then draw a triangle, use Pythagorean theorem to label it, and then fill in, go back and fill in what you need, whatever ratios you need. That process can be used to find the derivative of all 6 inverse trig functions if you would like, okay, if you want to derive those for yourself. I'm going to go ahead and give you the other 5 trig inverse derivative formulas. One thing I want to add here, though, is if you notice, all of these are written with a u in here. Remember, u is a function of x, represents u substitution, or a composition of functions. So while this first example was just tangent inverse of one single x, we do need to account for how we would handle if there was something else inside the function with the x. So for example, if that was tangent inverse of x squared, or tangent inverse of sine x, or something like that. Okay, so let's make a note here that we are doing this with compositions okay, or potentially with compositions, meaning we're using the chain rule, okay? And chain rule just means that after we take the derivative of the outside function, which for each of these is the inverse trig function, we will then multiply by u prime, okay? All right, so tangent inverse, we already have that derivative. That's the one we developed. So 1 over 1 plus, now I'm going to write this in terms of u, so 1 over 1 plus u squared times u prime, okay? Sine inverse is 1, has a derivative of 1 over root 1 minus u squared times u prime. And then secant inverse of u has a derivative of 1 over the absolute value of u times root u squared minus 1, and then times u prime. Okay, so a couple things about this. These two right here are similar because they both have the radical in the denominator, and the way that I remember which one is which is I remember that secant has an extra u in the denominator. It does need to have absolute value bars unless it's an expression that cannot be negative, but secant inverse derivative has an extra u down here, and then I remember that these two u's are right next to each other, like they're kind of up against each other. So this is not like a strong mathematically relevant way to remember which is which. It's just how I remember which derivative or which radical goes with which derivative, okay? So I remember that these two u's are up against each other for secant, and that secant's the one that has a u absolute value of u on the outside, and then we have root 1 minus u squared, okay, in this order for sine inverse, okay? Now, the cofunctions here are a little bit easier to remember if you can remember these three, and that's because these three derivatives are just negatives. So the derivative of cosine inverse is negative 1 over root 1 minus u squared times u prime. Cotangent inverse has a derivative of negative 1 over 1 plus u squared times u prime. And cosecant inverse has a derivative of negative 1 over absolute value of u times root u squared minus 1 times u prime. Okay, so if you can memorize these three, then these three are easier because we can just put a negative in front if the function starts with a co. All right, so let's go through a few examples. For each of these, if you would like to write them in terms of u so that you can do the full u substitution with the chain rule, that's totally fine. I'm going to identify u for each of these, but I'm not going to write it in terms of u. All right, so we have y is equal to tangent inverse of 3x. So because of the composition, this would be our u. Y prime is equal to 1 over 1 plus, and then u squared is now 9x squared. But then we need to multiply by u prime, which is 3. So moving that 3 over, we have 3 over 1 plus 9x squared. Okay? For this next one, we have sine inverse of cosine. So here, cosine is operating as u. Y prime is equal to 1 over root 1 minus u squared, so 1 minus cosine squared, times, and then u prime is going to be negative sine x, okay? So we end up with negative sine x over, now down here, 1 minus cosine squared x is the same thing as sine squared x, that's Pythagorean identity, so I can write that as root sine squared x, which is the same thing as sine, and then I have negative sine over sine, which is equal to negative 1, okay? For this one, we have secant inverse of e to the 2x, so e to the 2x is operating as u. For y prime, we have 1 over u, absolute value of u. Now here's the thing about this one. E to the 2x can never be negative, so I don't actually have to put the absolute value bars on there. It is not incorrect if you have them, but they are not required. If you're looking at a problem in the book, it's probably not going to put absolute value bars on there because it's a little bit redundant, but it does not hurt for you to have them there. And then root e to the 2x squared, which is e to the 4x minus 1, and now I need to multiply by the derivative of e to the 2x, okay? That has another composition in it, so using the chain rule, I'm going to have e to the 2x times another 2, all right? In this case, I can cancel out those e to the 2x's, and I have 2 over root e to the 4x minus 1 is my derivative, okay? For this last one, my function is cotangent inverse of x, but then that whole thing is cubed. In other words, if I'm using u substitution, this is u cubed, and when I take the derivative using the chain rule, I need to start by taking the derivative of u cubed. So my derivative of u cubed is 3u squared, meaning y prime is going to be 3 times that quantity, cotangent inverse of x squared, and then times the derivative of cotangent inverse of x, so times u prime. And so that would be times -1 over 1 plus, and it's just a single x in here, so 1 plus x squared, and I don't need to multiply times the derivative of x because that's just 1. So combining things a little bit, we get -3 times the quantity cotangent inverse of x squared over 1 plus x squared. Okay, now a couple things about notation and such. If you prefer to use the arc notation, so if you prefer to write arc cotangent of x instead of cotangent to the -1st of x, that's fine. Cotangent inverse is not actually raising it to the -1st power in the same way that like e to the -1st or x to the -1st is. Because the difference when we write this -1 looking exponent is that we're saying the inverse function, meaning we're actually switching where the ratio becomes the input and the angle becomes the output. So if it's confusing, especially if you have multiple exponents, to use the -1 as, you know, in the spot of an exponent, then go ahead and use the arc notation, and that's totally fine. One thing you cannot do is you cannot combine that and call it cotangent to the -3rd, okay? Because this on the outside means we're multiplying this by itself 3 times, but having a -3rd exponent means that we would be moving it down to the denominator. So please be careful about the difference between inverse notation and reciprocal notation.